Hey everyone, welcome back to Probability Theory. This will be lecture 2 of the course. And in this section, kind of as a precursor for formally defining probability, we need to do a quick review of set notation, set theory and set notation. So let's go ahead and jump into it. We'll call this section 1.2, just a review of set notation. So many people will have seen set theory here and there. It gets used, obviously, foundations of mathematics, but it gets used, it gets brought up in various different courses that you will take. And here I'm assuming most people will have seen much of this, but I just want to do a quick review just to level set in the cases where people maybe are rusty on this stuff. So we'll start with just, and again, this will be kind of brief, kind of rapid. So if you do need a more thorough review of set theory, if these concepts don't come back to mind quickly and in good shape, then yeah, you might want to spend a minute looking elsewhere for something more thorough. But we denote the set A containing elements A1, A2, and A3 as this. Right, so this is the notation we'll use: A1, A2, A3. This is the set of elements A1, A2, and A3, commonly referred to as A. Right, so this is the set A. Okay, and so this will be, I think this might be roster notation, I think, in set theory they call this. We'll have a notion of the universe of elements. So the universe of elements, or all the elements under consideration, will be denoted by S, right? And so for probability theory, that S is very, we'll see why we choose the letter S later. But this is, so in a particular problem, if we can define a universe of elements, right? A universe of elements, we'll denote that entirety of the universe using the letter S typically. Okay. The idea of a subset will be useful. So A is a subset of B. A is a subset of B. And we denote it A and then subset of B. If every element of A is an element of B, of course. Okay, so let's say that A is equal to 1, 2, and 3, and B is equal to 1, 2, 3, and 4. Then A is a subset of B because 1 is in A and 1 is in B, 2 is in A and 2 is in B, and 3 is in A and 3 is in B as well. Right, now B does have this extra element, but that's all right. A is a subset of B. Okay, so again, and then we do have this is I guess technically this is what we would call a proper subset, right? Because there is an element of B that isn't in A, right? So sometimes you'll write A as a subset of B like this, which means it can be A and B can be identical. So this is typically used as subset, and then A subset of B like we have up above is more like a proper subset. Okay, so just note that there is some distinction there. All right, now the idea of the empty set will come up. The empty set, or null set, is the set containing no elements. So very often we will see, we'll have a problem that involves the null set or an empty set, right? When when as we're kind of working through probability theory. So this is typically denoted using kind of a symbol like this, or occasionally you may see this, just kind of a roster notation with nothing on the roster. You'll also frequently hear people just write or say null set to indicate the empty set. Okay, right, so these are just the basics of set theory, and probably you will have seen this stuff, which is what I'm hoping. I'm hoping this isn't brand new. The next thing to bring up is the Venn diagram. So the Venn diagram can be used to show the relationship between sets. Can be used to show the relationship between sets. Now we'll use it frequently when reasoning about set relationships, right? So as we get into some problems, we may have to think about set relationships, and in doing so, we will rely on Venn diagrams. And so let's take a look at a few examples here, just to refresh our memory. If I want to talk about showing A as being a subset of the universe, right? So A being in the universe, right? Here's my universe S. Typically, the universe is sort of denoted using a rectangular shape. I don't know what it is, not necessary, but it's just kind of typical. And then the sets inside the universe are more frequently described using circles. Okay, so this is A as a subset of the universe. Okay, now maybe instead I want to visualize A as a subset of B in the universe. Right, so I can start by drawing my universe here, and then I draw B, and then somewhere inside of B I've got a set A. So this would be A as a subset of B. Right, so it's clear from the Venn diagram, right, that the set A, i.e. the circle that contains the letter A, is entirely contained inside the circle denoted as B. Right, so the idea being that everything that's A is also inside B. Right, now there are lots of ways to draw A as, to depict A as not being a subset of B. One way to do it would be to have A and B overlap, but not to have A entirely inside of B. So here we would see that A is not a subset of B. Of course, you could also draw it like maybe they have no elements in common. Right, so A is over here and B is over here. Right, either way, we see A is not a subset of the set B. Okay. All right. The next item that'll be important is what's called the union. The union of A and B. Right, and this is denoted as A union B. Sometimes this is said A or B. Right, so this is the notation for it, A or B. So the union of A and B is the set of all points in A, in B, or in both. Okay, so if you're in the union of A and B, then you're either in A, or you're in B, or perhaps you're in both, right? And so to see that with a Venn diagram, we take our A and our B, and they overlap some. In this case, they don't have to. But the union then is everything that's in one or the other, or both. Okay. All right, and maybe a concrete example here would be, let's let A equal 1, 2, 3, and let's let B equal 2, 3, 4. Then A or B is equal to 1, 2, and 3, everything in A, and everything in B, so 2, 3, and 4. So I just really need to add the 4 there, don't I? So the union would be 1, 2, 3, 4, whereas A and B are not identical. They're 1, 2, 3, and 2, 3, 4, respectively. All right, that's the union. Okay, and now recall the other one is what's called the intersection. The intersection of A and B, right? And the notation for intersection is similar. It's A and B, right? So instead of a cup, we have more like a cap here. So A and B. So the intersection of A and B is the set of all points in A and in B, right, at the same time. Okay, and so if I were to draw that, if I've got A over here and I've got B over here, well, they share some elements, they have some common elements, and that is the intersection. Right, so that right here is A and B. Okay, so our same example from before, if A is equal to 1, 2, 3, and B is equal to 2, 3, 4, then the intersection of these two sets, A and B, is equal to 2, 3. Those are the elements that A and B have in common. All right. Very good. So the intersection, the union, those will be very important for our probability theory examples and our definitions. The other item that's important is the complement. The complement of A is the set of all elements in the universe, in S, that are not in A. Right, and so we denote this, as A with a superscript C, a complement, or it's frequently denoted as A with a bar on top. I've also seen actually A prime. That'll happen as well. I think I'll probably veer towards this one mostly. So let's see, what does that look like? Well, so I've got my universe here, right? And then somewhere inside of here is A, and then a complement is basically everything that's in the universe that isn't A. Okay. All right. Something that's fairly obvious, if you spend a little time on this, or just a moment, this will be enough right here. If this is A, and everything outside of A is a complement, then it should be pretty straightforward that A or a complement is equal to the universe. Basically, everything is either in A or not in A, right? It's a binary there. So A or a complement must be the universe. All right. Very good. Very good. The concept of disjoint sets will be important. We'll need that. So we'll say two sets A and B. So if two sets A and B do not overlap at all, right? So if two sets A and B do not overlap at all, and I'll say, that is, i.e., they have no common elements. They have no common elements. So if two sets A and B do not overlap at all, we say they are disjoint, or synonym, mutually exclusive. Right? So they are disjoint or mutually exclusive. Those are synonyms. Right? And so just to kind of visualize this, we've got the universe here, and we've got A over here and B over here. Notice they do not overlap. They have no common elements. There are no elements that are in A and in B. Right? And so for this reason, you can say also that the intersection of A and B is the empty set in the case of disjoint sets. So A, B disjoint implies A and B equals the empty set. All right. Very good. So again, I'm kind of ripping through this. The point here is just to kind of bring these topics back up to the surface if it's been a while since you've seen them. And also kind of to settle on some common notation that I can stick with in case in the unlikely case that you've seen other notation. So another item of importance will be what are called the distributive laws. The distributive laws of set theory. Right, so what do they say? Well, there's two of them. The first one says that the intersection of A and the union of B or C, right? So I got two sets, A, and I've got the union of B or C, and I'm talking about the intersection of those two. The intersection of A and B or C is equal to the intersection of A and B or the intersection of A and C. So it's called the distributive law because you can think of it like distributing, right? So if this was x times y plus z, you would know how to treat that. And similarly, you treat the distributive law of set theory, right? So A and B, and then or A and C, right? So it's almost exactly the same as the distributive laws that we're used to from arithmetic. Okay, and then the second one just kind of uses the different set operations. So A or B and C, right, and you get the same pattern. So A or B and A or C. Okay, now these are fairly easy to prove. We're not going to do it in this section, but it is fairly easy to do. You just simply assume an element's in here, and you break apart what that means, and then you find that it's also in here, right, for an arbitrary element, and so that works. We won't prove these, but it is useful and instructive kind of to see maybe what these look like in terms of Venn diagrams. So let's take one here. So let's say I have three sets, A, B, and C, right, and they kind of overlap in this way. Then this first piece here, A and B or C, right? So that means I'm in A and I'm in B or C, right? And so if you think about what that means, that's really this section here. That's that piece right there, right? So this kind of shape here is your A and B or C. Now, what the law says is that that's equal to A and B or A and C. Well, where's A and B? Well, that's this part here, isn't it? And where's A and C? Well, that's this part. Right? And so if I say it's equal to A and B or A and C, it's either this part here or it's this part here, or possibly both. Right? And so that's all the distributive law set theory is saying in this first case. Okay. So very useful to try to visualize these things. Take the time to try to visualize the second one as well. Okay. And then the last item that we want to review here is De Morgan's laws. So De Morgan's laws, and this will be important as well, we'll use this quite a bit, says that A and B complement, so the complement of the intersection of A and B, is equal to the complement of A or the complement of B. All right. That's the first one. The second one, similar pattern again, is A or B, the union. The complement of the union is equal to the intersection of the complement. So A complement and B complement. Right, so here I've got the complement of the intersection is equal to the union of the complements. And here I've got the union of the complements is equal to the intersection of the complements. So that's interesting. Let's take a look at this second one here. In this case, let's bend this out. And so here I'm going to draw the universe in because I need the background. So say I've got A and I've got B. All right, so this first set is A or B complement. Well, I know A or B would be everything inside the circles, so the complement of that is everything outside the circles. Okay, and then De Morgan's law says that that's equal to the intersection of the complements. All right, so what is that? So let's first take this piece here and draw it. What does that look like? All right, so I've got my A and I've got my B. And so this is just the complement of A. So that's everything outside of A. Right, so a good chunk of B is out. Right, so this is A or B complement here, and this is A complement. So what does B complement look like? So again, I got my A and my B. So B complement is here, and that's just everything outside of B. All right. But De Morgan's law says that I need the intersection of those two. So what's in both? Well, it's helpful if I actually shade what's in both, right? So what's in both is this piece outside. Right, so I've got that part there, right? Basically everything that's outside the union. And then over here, it's the same, right? That part is in both as well. Right, and so you can see that the intersection is this section outside, right? Which is exactly what is said in the first part. Okay. All right, very good. Very good. Okay. So I think that's where we'll stop. A few other miscellaneous set theory items might pop up in the course of the class, and if they do, we'll deal with them on the spot. I think this will probably cover the big items, the main items. So if you want, spend some time trying to prove a couple of these. It's useful just to kind of get your proof gears working a little bit if you haven't done that in a while. But I think we're now ready to go ahead and start talking about the actual probabilities. So next time, in the next lecture, we'll lay out a kind of probability model for discrete types of probability. So up next, probability definitions and a model. Okay, so until then, take care.